All right, so as I was just talking about in the last film, or the last video, suppose you started with, 1 gram of radioactive, it's automatically radioactive if it's uranium-238. Anyhow, what we do is we know that if one half-life has gone by, then you're only going to find half a gram of uranium-238, and you're going to find the other half to be lead-206, because that's what it ultimately becomes. So if it was less than one half-life, there would be more uranium. If it was more than one half-life, it would be more lead-206. So what we do is we dig all around the Earth, and we find uranium-238, and every time, this is the key thing. Like, suppose you just dug into the Earth once, you found some uranium-238, and within that rock there's exactly the same amount of lead-206. Well, that's one instance, but that's not how you can tell the age of the Earth. The way that we know this is when we dig all around the planet. Every single time we find uranium-238, you get half lead-206. Every single time. Tens and tens of thousands of times have we dug and we found that. And this doesn't just work with uranium. That just happens to be the one that I'm talking about. There's another form, a long-lived radioactive that has a long half-life, like, for example, potassium-40, and you get the same thing, the exact same date that the Earth is 4.5 billion years old. And not just that, we get the same thing with the rocks from the Moon, from rocks on Mars. We get the same kind of thing. All right, so we know the half-lives. It's very well known. And so using the half-life of uranium-238, that's just one example, we get that the Earth is 4.5 billion years old. And in fact, we believe the whole solar system is 4.5 billion years old. All right, so yeah, there's the lead-206. I guess I should have slid down a little bit to show you this. All right, so good. So now the crust of the Earth is changing over time. For a long time, humans thought that the continents were always at the same locations and they never change. Really, about roughly, 70, 80 years ago, some geologists said, "Well, hey, wait a second. Look at the eastern side of South America and the western side of Africa, and they kind of look like they fit together like a jigsaw puzzle." And people, of course, at first when this was proposed, they were like, "Oh, this is crazy. There's no way that that's true. The continents have always been there. There's no way that they've been moving apart." And the other thing that besides the geological evidence, there's actually fossil evidence that animals about 220 million years ago on the what we would now call the eastern side of South America and the western side of Africa, or this part of Africa here, that 220 million years ago they were the same animal. Right, so exactly the same animals, we find fossil evidence. And then as the continents drifted apart, South America and Africa in particular, as they drifted further and further apart, the animals evolved in different directions. So then, let's say, 150 million years ago, you see completely different animals here, on the eastern side of South America, and then compared to the western side of Africa. All right. So that's this has become more and more accepted that the plate tectonics is happening. In fact, we know that right along the middle of the Atlantic Ocean is what's called the Mid-Atlantic Ridge, and this is actually goes right through the middle of not the middle of Iceland, so part of Iceland, and so this is actually causing the continents, the North American continent and South American continent and Africa and the Eurasian continent are actually moving apart from each other, right? And so, and then of course there's some other evidence of this. For example, the Indian continent here, the Indian plate, as far as the plate tectonics go, is actually crashing into the Eurasian plate, and where we see that happening are the tallest mountains in the world, right? The Himalayas, of course. And, and of course, anywhere the plates are smashing into, one plate is smashing into another plate, you have earthquake activity and also volcanic activity, of course, that extends through the Andes, up through the Rockies, and then extending on the other side of the world, through Japan and Indonesia. And that, in fact, if you look at the world like that, they call that sometimes the Ring of Fire, because there's lots of activity where the continents are smashing, or the plates, the continental plates are smashing into each other. You have volcanic activity and you have earthquakes. All right. So let's talk about that. There's two terms here we need to talk about: subduction and rifting. All right, which we actually just talked about rifting and subduction, for that matter. So when one plate slides below another plate, that's really what's called mountain building, or subduction anyway. And you have some mountains occurring. Sometimes there's volcanic activity as well. All right, so yeah, that's of course what the mountain building is all about. And there's of course India, showing the Himalayas. All right, and there's of course the fault lines when one plate is moving in a different direction than the other plate, and there you have earthquake activity. All right, and here's rifting. As I mentioned, probably the best evidence of this is along the center of the Atlantic. This is sometimes called the Mid-Atlantic Ridge, and it's not moving. It's not separating greatly. It's only like a few centimeters per year that it's doing this. But over billions of years, you have thousands upon thousands of miles of ocean in between Africa and South America, for example. All right, so so what about magnetic fields? And I guess that's the other thing, is we can actually when there's new eruptions, and there's metal fragments, metals that are affected by magnetic fields. Not all metals are, but for example, iron is probably the best example of that. So if there's some iron on a lava flow, what happens is that iron, when the lava cools, will orient itself, align itself to whatever the magnetic field is of that time, of that particular time. And so geologists have been digging this up for many, many years now, and we find that, in fact, the magnetic fields of the Earth have reversed over time. They're not always in the same. So, the North Magnetic Pole and the South Magnetic Pole switch sides every so often. And that's actually not well understood why that happens. We do have evidence that it does happen, but we're not exactly sure why. Of course, we know that the plate motion is driven by convection, right? The heat rising and then falling, rising and then falling, the heat in the mantle, of course, rising and causing the plates to move. All right, so this is of course a good example of convection. Hot material physically rises and then it cools off and falls back down. Hot material. All right, so that's convection. Some examples of convection, of course, are water. When you boil water, that's a convective process. So we think that in fact, some scientists have named this long ago, that all the continents were actually one giant supercontinent about 220 million years ago, and that was called Pangea. That's just the name of it now. And of course, it's been breaking apart ever since. And of course, you get this is the modern world. So it's 65 million years ago, about the time the dinosaurs all died off. The Earth kind of looked like this, and then and this is not fixed, right? This is just how it is in the present. Millions of years from now, the continents will have drifted in different directions. Of course, nowadays we actually measure this motion, and we can predict where they're going to be. And what about this thing called the magnetosphere? And again, this extends way beyond the atmosphere of the Earth. What's important about this? Let's talk about magnetic fields for just a moment, right? So a magnetic field is caused by moving charge. Current is the name of moving charge. Now, where do those moving charges come from? For the Earth, it's inside of the Earth. It's the liquid. The liquid core is moving around, and metal, of course, becomes charged very easily. So the metal core moves around at a different speed than the surface of the Earth, and that causes a gigantic magnetic field. Now, it's not the strongest magnetic field in the solar system. Of course, the sun has the strongest of them all, and then Jupiter has the next strongest field. We'll talk about that as we move throughout. Anyhow, so that's the cause of magnetic fields, is current. Right. Or sometimes it's called the dynamo effect. Now, what happens is you have what are called charged particles, also known as the solar wind. So these are protons and electrons that come off that are very energetic and come off the surface of the sun, and that's called the solar wind. And that's heading out into space in all directions. And so sometimes, of course, the solar wind is more powerful than other times, and this thing called the solar wind, again, it's charged particles, and we know how charged particles interact with magnetic fields. They basically will spiral around the field lines, and that's actually exactly what happens with the Earth's magnetic field. Now, the solar wind would actually be a dangerous source of radiation, and it is, in fact, a dangerous source of radiation, but we have this natural protector, that is the Earth's magnetic field. And so what happens is these charged particles get trapped in the Earth's magnetic field, and they get usually either deflected around the Earth, so they never hit the Earth, or if they do hit the Earth, they are deflected just to the north or south pole. I'm pointing at the wrong thing. Either to the south pole or to the north pole. And so when they hit the Earth, they heat up. When they hit the atmosphere, these charged particles will heat up when they hit the atmosphere, and that's really what the source of what's called the aurora, right? That's the aurora borealis in the north and the aurora australis in the south. All right. Another thing that we know, this happens way out in space, is sometimes these charged particles will get trapped within the magnetic field and basically bounce back and forth, and they're doing this in like a shell, and these are called the Van Allen belts. These were actually explored by a spacecraft called Explorer 1. They were predicted first, and then of course discovered. This was the first spacecraft that NASA sent up into space. All right, so here are the Van Allen belts. The northern lights or the southern lights, or auroras, as they're also known.